All right. So our objectives here today are going to be to write the equilibrium or ionization constant expression, Ka, for a weak acid, to tell the meaning of Ka, and to describe an acid-base buffer solution and explain how it works. And so walking out of here today, if we give you a weak acid formula, you're going to write the dissociation equation and a Ka expression. And then we're going to explain what the size of Ka has to do with the strength of the acid. And then we're going to explain buffers and how they resist change in pH. And we'll talk about how they react either with the acid that's weak or its conjugate base. All right, so we have 6 strong acids. Raise your hand if you can give me all 6. All 6 strong acids. Yes, let's go with, let's see, you are potassium? All right, potassium. Awesome, give me the formulas. Okay. Awesome. Okay, so everything else, as far as we are concerned with our test, is going to be a weak acid, right? So we've got lots of weak acids. And so what is going to be the deal with weak acids? Because we know that strong acids dissociate completely, weak acids only partially dissociate, but they can't all be the same, right? There's going to be different amounts of molecular attractions that are involved with each of these, and so water is going to pull a little harder on some than on others. And so because they are not the same, we have to have a way of saying how much they break apart in our solutions, right? So they're not all the same. We are going to use Ka to help us understand how much they break apart. Okay, that's what this whole thing is going to be telling us about today. All right. So we know our formula basically is, hey, we have an acid and it's going to be put into water. And when it gets put into water, it's going to create a hydronium ion, a positive ion, and it's going to create its conjugate base, which is basically going to be that component that will create the negative anion of the salt, right? And so we can write an equilibrium expression with this formula. This is the dissociation equation, right? That's basically telling us what our dissociation is. And so we can say, all right, well, if that's our dissociation, what's our K for that? And we learned about K in the previous chapters, right? And so it says, hey, take our products, hydronium ion concentration times the salt of that ion, or the conjugate base, and divide it by our original acid we had in the reactant side. Now we do not have H2O here. Why do we not have H2O here? Hands if you've got it. Why do we not have H2O? Okay, excellent. That's right. 10. It's because it's a liquid, okay? H2O at the bottom here because we don't include liquids or solids when we do K expressions, right? All right, so this is called our K sub A, or our acid ionization constant. What does it do? It tells us our strength of our weak acid. The bigger the Ka, the stronger the acid, okay? The bigger the value that you get for Ka, the stronger the acid. Remember, we learned about Kas, or not Kas, but we learned about Ks before, and we learned that bigger numbers are going to indicate higher concentrations, right? All right, and that's because, if you think about it, if I have the hydronium ion in the numerator, right, and I got the hydronium ion being like the main component of what creates an acid, then if I get bigger Kas, it's because I got lots and lots and lots and lots and lots of hydronium ions. The more hydronium ions I have in my numerator, the bigger my K value is going to be. And so that K can tell me the strength of the acid. More hydronium ions, the stronger the acid. Questions on that? Okay. So let's look at phosphoric acid. Phosphoric acid is the stuff that you guys see in your darker sodas, your Cokes, your Dr. Peppers, things like that. Now, this is a weak acid. And so we have a dissociation equation we write with it. The H3PO4 turns into H2PO4 minus. Don't forget about your little minuses up there. Okay. Then it's also going to give you the product of an H3O plus. So we're going to make a hydronium ion, which of course is basically the root of what all of our acids are, right? And so now we take our hydronium ion times our conjugate base, okay? And then we end up dividing that by our original weak acid to get our value for K sub A. You should now be able to do the same thing with acetic acid, another weak acid. So go ahead and write out the dissociation equation and the K sub A expression for HC2H3O2. And we'll call on somebody to answer it here in a second. Water's good.
Mr. Bowers, do you have multiple games a day during the day or one each day?
Okay, let's see if you came up with the dissociation equation strontium.
Plus H2O. And then the double-sided arrow.
Good.
H3O plus, and then plus C2H3O2 plus.
I need something on that one still. You gave me a plus, and I don't like that. What do I need to have on this one? Yeah, right, because it lost a hydrogen, it lost a positive charge, and so we now have a negative charged ion that's there, right, an anion. I need my states of matter. Okay. Okay. Aqueous, and then aqueous, okay? Yeah, so only thing in this case that's not going to be aqueous is this H2O, which is one of the reasons why we don't include that ionization constant expression. Okay, so selenium, let me see, let's get that final Ka. Good. C2H3O2 minus in brackets. Okay. Okay. HC2H3O2. And in brackets, because we're doing concentrations of each of those. All right, good job. Got that right. Okay, good. We're all in the right spot. Good job. So now let's go ahead and see, with a little turn and talk, if you can tell me which of these is representing the Ka expression for hydrochloric acid. Okay, so turn and talk, and I'll call on somebody.
Did you ever hand Is it anything?
Yeah, it should be in there.
But doesn't the products go on the top? No matter how. Doesn't the products go on the top? It's still
Products do go on the top, though. Products divided by reactants. Huh? Well, you have to do your dissociation equation, right? So what is your dissociation equation going to say? You're starting with that.
So, I didn't even know that helps because it would be like HCl and then goes to H3O plus Cl. So A would be.
Yeah. All right. This is for fluorovium, phosphorus, and germanium. Together, you guys agreed that it is what? Fluorovium, phosphorus, and germanium.
Oh, it's
A? 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 Okay. Yeah, absolutely. Right? This is your reactant, right? Hydrochloric acid. And remember, it's products over your reactants. So there's none of these have, except for that one, has the HCl in the denominator, right? So then you got to double check. Is this gonna? Could it be none of these? Well, your products are going to be H3O plus, and then your ion, which is left over from that HCl. And so you are looking at A as your correct answer. Okay. All right. Good job for all. Let's go ahead and now talk a little bit about what these strengths mean, right? The Ka. How big is the Ka and what does that mean? I want you to notice that here we have our formulas for our acids. Here we have our formulas for our bases, okay? And you can see that at the top, a hydronium ion has a Ka of 5.53 times 10 to the first. And we go down to water, we have a Ka of 1.81 times 10 to the negative 16th. So which of these values, the ones that are up at the top or the ones that are at the bottom, are indicating the stronger acids? Is it the ones at the top or the ones at the bottom? This goes to calcium. Because? Because? What did we learn? Did you write in your notes about the Ka? The something, the Ka, the something, the acid. Okay. Yep. And what about that acid ionization constant? Is that if it's bigger, is that a stronger acid, or is that a weaker acid? Yeah. The bigger Kas are going to be the stronger acids, right? And so 5.53 times 10 to the first is a bigger number than 1.81 times 10 to the negative 16th. And so this hydronium ion is a much stronger acid than the water is. Okay. And of course, that makes sense, right? Because hydronium ion is essentially what acids are all about. And so water would not be a very strong acid, but hydronium ions would be. Now, this whole thing is, relative strengths of acids and bases. Some of these are strong, some of these are weak. Really, what we're looking at when we look at all of these things, though, is a bunch of weak acids, okay? The only one you might be able to think about as strong, in a pure form, you might be able to think of it as a hydronium ion in a pure form, or a hydroxide ion as a strong base in its pure form, right? But everything else is going to be essentially a weak acid. So the stronger an acid, the weaker its conjugate base, which if we look at this H3O plus, if that's a stronger acid, then its base, H2O, is pretty weak. Okay, that's not a very strong conjugate base. It's a weak conjugate base. Here I have a weak acid, right? If that's a weak acid, then my base is probably going to be pretty strong. My conjugate base is going to be strong. So as you increase in the strength of one, you're decreasing in the strength of the conjugate. Okay? Questions on that? That's a good question. No, it's not always about adding up to 14 because you're not necessarily going to get those things to add. The conjugate base, right, yeah. So they don't really necessarily add up to 14. The conjugate base and the acid won't necessarily add up to 14. They might have their own, pH values depending upon how they interact with the solution. Okay, so let's talk about buffers. Okay, now you guys know that buffers are everywhere around you, but especially inside you is some buffers that are most important. And the buffers in your blood are preventing your pH from varying too much. Your pH in your body, in your blood, has to stay, I think it's like between 7.25 and 7.35. It has a very small range that it's allowed to move back and forth between. And so your body has these buffers so that if you have too much of one particular type of food or something that is trying to raise your pH, or if your body is going through something like asphyxiation, or you're hyperventilating, then your pH in your blood is going to be changing. And so it's trying to keep your pH in your blood from changing too much, because if it changes too much, you die. And so a buffer is defined as a solution that resists changes in pH when I add an acid or a base. Okay, now obviously if you add a bunch of acid or a bunch of base, you're going to change your solution. You can't completely stop something. But if I have small little changes, those small changes are going to be giving us no or very little changes in our pH. Now your buffers are made up of two components, right? Your buffers are made up of a weak acid and the conjugate base, or the salt. Okay, so buffer is made up of a weak acid. Strong acid, yes? No, weak acid, right? So one of the things you'll look for is this a weak acid? And it's made up of the conjugate base of that weak acid, okay? Or basically it's that salt. So if we think about it, the weak acid component of a buffer is able to absorb added base. So here's our weak acid, HA, okay? Now, if I put some base in there, what's happening is that base is going to take the H and make water. Well, water does not have a very low pH, right? Water's neutral. And so if I can take something that's acidic or basic and change it so that it's not either of those, then that's going to be a buffer. In this case, it's taking a base, which would normally make our pH go up. And instead of making it go up, it's like, oh, here you gave me base, I give you water. Psh, okay, easy. Now it doesn't have much of a pH change. Now it also has this little ion here, right? That's the anion, that's the salt component. But remember that salts, when they come together, just like we learned about before, like sodium chloride, doesn't really have a pH in water, right? And so what you're doing is you're taking something that has a base like hydroxide, which is a strong base and it could change the pH a lot, doesn't change your pH much at all. Your conjugate base, or the salt, here's my little salt, my anion, okay? Now what happens if I add an acid? Well, all right, add an acid to the salt, and it's going to take the H from the hydronium, which is the acid, and it's going to be like, okay, I'm going to make a weaker acid. Remember, hydronium is kind of like the strong acid, right? I'm going to take the weaker acid now instead of the strong acid. Here's strong. I'm going to replace strong with weak. And guess what? I'm going to give you water. Again, not much of a pH change. So whereas normally you put in some strong acid and you see the pH drop a lot, doesn't drop much. Why? Because I just replaced it with a weak acid and some water. And the weak acid does not hold on or does not dissociate completely. And so some of those particles will come apart, but not many of them. And so there's not a whole lot of breaking up. Okay, so let's see what this looks like in terms of numbers. Here in this example, I took 0.1 molar hydroxide and I got a pH of 12. But if I have a buffer solution in there and I take that same 0.1 molar hydroxide, it basically stayed at a 5. In this example, I took 0.1 molar hydronium ions, so strong acid, and it was something that made it go all the way down to a 2. And this one basically stayed as a 5. Didn't change it much at all. Okay? So what you can see is that whereas in one example with pure water, I can change the pH drastically, but if I put it into a buffer solution that already has a weak acid and its salt, it doesn't change the pH much at all. Okay? Here's another example. Here's a buffered solution. How do I know it's a buffered solution? It has a weak acid and it has the anion of that weak acid, the conjugate base, right? It's the salt of that conjugate base, basically. All right? And so if I have that initial buffered solutions and I add hydroxide to it, it's going to form a weak acid. All right? Hydroxide is a strong base. Okay? And what are we doing? We're going to transform it so that it has something different, right? HF plus the hydroxide is going to turn into water plus the F minus, okay? And so it's not going to change. So notice how my HF is lower here compared to my F minus. And so that means that the pH did not change a lot. Even though I added hydroxide, it did not increase the pH much at all. And then over here, I add the hydronium ions. Does that increase the pH much? No, because even though I added hydronium ions, it combined with the fluorine, and so it took a strong acid and it turned it into a weak acid. And so I've got a low amount of increase because I have a weak acid that is a greater amount of product there, but it does not have nearly as much of an impact to my pH as my strong acid does. Okay, so this is how you can use a buffer to prevent pH changes. Questions on that? All right, that one is a little bit tough, all right? There's a lot that is kind of packed into that one. So I want you to make sure that you look through those and understand them, because I think sometimes we can get a little bit confused by what we're seeing here. So make sure you understand how that process is working. If not, then please ask me, okay? All right, so another turn and talk. You have to figure out which of these 4 choices represents an effective buffer solution. Which of these is going to be an effective buffer solution? And talk with your neighbor, and then I'll choose a group of you again. All right. Let's see if this group can give us an answer. Thallium, calcium, and germanium. What do you think? B, what do you think? Also going with that? Going with that? Okay, so you guys have to describe why you think that's the correct one if you think it is. Awesome. HCl, strong acid. So those two get canceled out. Love that, because it can't have a strong acid. It has to have a weak acid, right? Good. Well, that still leaves me B and D. Can you eliminate any of those? What's that? Okay. They both have potential conjugate bases if you do their dissociation equations. These would both be reasonable conjugate bases for both of those. Oh, HClO4 is a strong acid? So we need to eliminate D. Yeah, so if you look at the ones you can eliminate the strong acids in 3 of those. And so, yeah, this is a weak acid, and then this would be its salt, right? That would be the conjugate base with the potassium, in this case, let's say, that might be in there to make a salt. Good job. So that would be the correct answer in that one. Now, I want us to look at a problem with calculating Ka, and then I want you guys to do this, because one of the things that we need to be able to do is figure out what the actual K value would be, or if we're given a K value, can we figure out the hydronium ion concentration? okay? So in this example, we can see that they give us the concentration of uric acid, which is a weak acid, and then they're telling us the equilibrium concentration as 3.4 times 10 to the negative third, and they want us to calculate Ka. And so we are being given the 0.110 molar as part of our reactants, right? That's the weak acid that we're starting with. And then it goes through and dissociates. And you'll notice that we have a 3.4 times 10 to the negative third for both of our bits there, right? And that is because that is our equilibrium concentration of H3O plus. And if we think about what we're going to have, there's a 1-to-1 ratio between the H and the A, right? Our HA is splitting up into the H and the A. And so we should have the same concentration of both of them. And so if we get the concentration of hydronium as 3.4 times 10 to the negative third, we should be able to figure out that the other one is going to be the same, right? All right, so what I want you to be able to do is calculate a problem just like this. So let's see if we can do this. I'm going to give you a your turn type of problem. And let's see, which one should we try? Let's see, what is, I feel like I want to do, sorry, deciding this one still. Let's just go ahead and do the one that is right here. All right, so find the pH of a 0.1 molar solution of HOCl. So this is one that is a weak acid now, right, instead of a strong acid. So it's giving us the Ka. We have to figure out the hydronium ion concentration, the H plus first. Once we find the H plus, then we can then figure out the pH. Are you with me? Okay. Give you a minute to work on that. Yeah, but we're now going to solve for the H plus, right? But the concentrations of these two would be the same.
So A minus and A.
And H plus should have the same concentration. These two should be the same, but that one won't necessarily be the same, right?
Would that one be, is that given right there?
Mm-hmm.
Okay, and then Ka is given, so we have to figure out H plus, which would be the same as A minus. Okay.
Mm-hmm.
Oh, mine just went blank. Oh, do we need to show gems for this?
You should be showing your gems, yes.
I'm a little bit.
Good.
Don't we have two variables here?
Yes, but those two things are going to be, this should be H plus, and this should be OCl. And then those two concentrations will be the same as each other, right?
Okay, so
And so that's going to be like a square value.
right.
And so then once you solve for this side, then you can figure out what it's like square root of.
I have it.
Okay, you guys ready for the answer? You might have been fast enough. If not, I apologize. You would have had this equation. You notice that the x squared here is a big part that hopefully you figured out. Those two are going to be the same. So then you could take that square root, and then find the answer for that one. Okay, and then you had to figure out the pH from there. Raise your hand if you got it right. Nice, good job. All right, so that's where we'll stop tomorrow.